Now, a rational equation or inequation is any equation or inequation that has a variable in the denominator of the rational expression. The process generally, whenever we have an equation involving fractions, the first thing we want to do is we want to get rid of those fractions in order to make the equation easier to deal with. So we do that, remember, by multiplying both sides of the equation by the lowest common denominator to clear away the fractions. We then solve the resulting polynomial equation, because we know polynomial equations are easier to do, to solve that is, and then we state the solutions, and we check for any extraneous values. Keeping in mind that if we have variables in the denominator, we have to be sure that those variables aren't causing the overall expression to be 0 in the denominator, which means they're undefined. So we'll have to check for those and perhaps reject some solutions. The solutions that we might need to reject are called extraneous roots. All right, so let's just jump right in and start with an example. A rational equation, we have a variable in the denominator. We're going to start by multiplying both sides of the equation by the LCD. And the lowest common denominator is 4x. So we'll multiply both sides by 4x. Remember, we have to distribute the outside term to both parts since there's two terms on this side. So we have to go 4x multiplied by 4 over x, 4x multiplied by x over 4, and 5 over 2 multiplied by 4x. All right, so the purpose now is to simplify this to a polynomial equation. X's cancel out, 16. 4's cancel out, x squared. And our 2 and our 4 cross reduce to 10x. Our resulting polynomial equation you can see here is a second degree, a quadratic equation. And we know to solve quadratic equations, we set them equal to 0. And the first thing we'll try to do is we'll try to factor the expression. This does indeed factor. X minus 8, x minus 2 equals 0. So we get x equaling 8 and x equaling 2. So we've solved our equation. And the final step is to ensure that neither of these values would cause the denominator in the original expression to be 0. So if I substitute 8 or 2 up above, that's not creating a problem. And these should therefore be our correct solutions. Okay? So there's the algebraic process involved in solving a rational equation. Now let's just spend a little bit of time with the graphing calculator and confirm that our solution is correct. And what we're going to do is we are going to go back to our original expression up here, and we're going to enter either side or both sides of the equation as two separate equations. So I'm going to enter y equals this expression and y equals 5 over 2 into my graphing calculator. Okay? So you can see I have that already pre-entered here. y1 equals and y2 equals. We're going to bring up the graph of both equations. There we go. And our solution, given that we're looking for where the two functions are equal to one another, that's going to correspond to the points of intersection of the two graphs. All right, so let me just find out the coordinates of these 2 points via the calculate button. So I'm going to intersect, move my cursor close to one of the solutions. I'm getting close to this one. Pick my graphs. y1 is the first one, enter. y2 is the second graph, enter. I make my guess, which means bring my cursor close to my solution, and I'm getting a point of intersection of 2, 2.5. All right? Well, the y is not relevant. The y is just the y value where the two functions is the y value that the two functions share in common, and they share that y value in common at the moment when x is equal to 2. So since there was no y in our original equation, x equals 2 is one of our solutions, and that of course is confirmed by the algebra we just finished doing. And similarly, you could do the same for the other point of intersection. Just bring your calculator close to that point, go through the menu options, and we get x equals 8. Now we're going to look at a more complex rational expression, one in which the common denominator is more complicated. If you can look at the denominator of this rational expression, we have three very different looking expressions. But we'll notice that over here on the right, we can factor the denominator of this rational expression. That would be x minus 3 multiplied by x minus 1. We have x minus 1 in common. Seem to have something close to common here. We have 3 minus x and x minus 3. Well, what we could do to make these two common is we could factor out of 3 minus x, factor out a negative 1. I'm just going to rewrite like so. What I'm saying is that this 3 minus x is equivalent to negative 1 times x minus 3. I can confirm that by distributing through, getting negative x plus 3. All right? And why would I want to do that? Well, I then have another section, another factor of the denominator that's common, which is going to make my finding of a common denominator a little simpler. All right, so let's clean all of this up. This negative alongside that negative is going to create this expression to be positive, and we're then going to have 2x over x minus 1 plus 4 over x minus 3 equals 5x squared minus 7 all over x minus 3 times x minus 1. All right. We now have things that are much more in common. Our lowest common denominator is going to be x minus 1 multiplied by x minus 3. And we're now going to take our common denominator. We're going to multiply both sides of the equation by that common denominator. X minus 1 times x minus 3 on both sides. Yes, there's a lot of writing involved, and you need to be very careful because it is quite easy to make a mistake with such a large amount of algebra happening. All right, we're going to take our common denominator on the left side, and since we have two terms in the brackets, of course, that means we have to distribute that over. On the right side, we have our common denominator multiplied by one full term. So this side, things are a little bit easier. On the right side, that will simply cancel out two fractions. We can cross-reduce the numerator and denominator, and we're left with 5x squared minus 7 on the right. On the left, this multiplied by the first term means that the x minus 1s are going to cancel out, okay, since this expression is over 1. So this fraction times this fraction, the x minus 1s are going to cancel out, and we're going to be left with 2x multiplied by x minus 3. And then we take our common denominator and multiply to the second term. This time the x minus 3s are going to cancel out, and we're left with 4 times x minus 1. We're now down to an expression, a polynomial equation, no fractions. So we will go through and begin to solve this equation. Let's multiply it out, and as we're doing so, we need to start thinking about what type of polynomial equation we have. Is it first degree? Is it second degree? Start looking at this. I've got a 2x squared and a 5x squared, and it looks as though I'm dealing with a second degree equation. It doesn't look like those squareds are going to cancel out in any way. So what I'm going to want to do is I'm going to want to set this expression equal to 0, because to solve a quadratic equation, that is the general way we go about solving it. Set it to 0 and see if it's going to factor. Now having my quadratic equation equal to 0, I'll look and see if I can factor it. Are there two numbers that multiply to negative 9 and the same numbers that add or subtract to 2? There are not. So we will need to use the quadratic formula to solve this equation. A, B, and C. So negative b would be the opposite of b, plus or minus b squared minus 4ac all divided by 2 times 3. So x is negative 2 plus or minus 4 plus 36 divided by 6. I'll now reduce the square root of 40 to 2 root 10. And then I can divide top and bottom of my fraction by 2 to negative 1 plus or minus 1 root 10 divided by 3. If you'll notice back on the original equation, the values of x that are not defined were x equals 1 and x equals 3. We did not get those answers in the solving process, so there are no solutions to reject. Be sure you bracket the numerator of your expression. And our second answer is the negative 1 minus that. So we'll make that change. 0.72 and negative 1.39 are our decimal approximations. In the last example, I used my graphing calculator to confirm my solutions. I'm going to do the same thing with this example. In my first example, though, what I did is I took each side of the equation and set those equal to 2 separate graphs in the calculator, and then I found the points of intersection for those. What I'm going to do this time is set my equation to 0. So I'll move the right side over to the left side. And then in my graphing calculator, I'm going to graph y1 equals this. And so I'll get a function of y with respect to x. Let's bring the calculator up. As you can see, I've got my equation. It takes quite a bit of space, but it's in there just as I've shown you. And I'm now going to graph. And I have one graph. And my solutions this time, since I'm looking for where y is equal to 0, those would correspond to my x-intercepts. So I'm getting an x-intercept in this neighborhood. Let's check out what that would be through the Calculate menu. You've used this feature many times for other things. And that's confirming a solution of x equals negative 1.38. And I can do the same for the other solution. Moving towards that, coming from the left side, coming from the right side. I'm confirming that I have an answer of, there we are, 0.72.